So the elements that we described so far are very good in modeling any regular shape. We are able to get compatible displacements. So far, we have achieved compatible displacements or compatible elements in both the linear version and the nonlinear version. And the integration, because remember, we are doing an integration of V transpose CB over the volume. This integration is actually, so this is, you perform V transpose CB. We're trying to model a two-dimensional domain. You're going to obtain a matrix that's 8, or degrees of freedom, multiplied by the degrees of freedom, integrated over the area. Now, this integration is done over dx dy for each element. Let's say we're talking about this element. This is x1, or x and y. So x is from negative a to a, and y is from negative b to b. So the integration domain is very simple. I can integrate on this element. Now the integration is done. I have, this K is an 8 by 8 matrix. It has 8 by 8 entries. Each entry is a function of x and y. And then I integrate this entry from negative a to a and from negative b to b. So I integrate, so I'm doing the integrations 36, so I'm doing it degrees of freedom multiplied by the degrees of freedom times. The degrees of freedom are 8, so 8 by 8. Now, this is fine as long as the domain is regular. If I have, once the domain is irregular, then I need a better method. First, I need an element by which I'm able to model an object that looks like this. Which means maybe this element will look like this, or aligned with my coordinate system, but some elements will have this shape. And the neighboring element will even have a shape like this, and I want, for this element and for this element, I want a displacement that ensures the following. Number one, I want to ensure that the displacement as I approach the side is equal to the displacement as I approach the side. And number two, for each element, I want to be able to integrate the x dy. But the problem now is, how am I going to do this integration? Let's say I'm doing the integration on this element. Well, dx changes if this is x and this is y. Basically, I want to integrate over this area, so I want to integrate if this is, so the bounds or the limits of the integration will be functions. It's not going to be easy to integrate over this area. And then each element, to do that integration, each element will require a lot of computations, and it's not going to be easy to do any program to do this integration. Perhaps if Mathematica, when FEA was invented, if Mathematica was available then, it might be you might be able to do this using Mathematica, but at that time, Mathematica was not available, so they need a way that is not, that is simple to do this, both computationally simple and also methodologically simple. So, for this reason, there are so many ways across the, throughout the development of FEA, there's so many ways to come up with elements to overcome or to be able to model a general shape and to be able to do the integration simply, in a simple manner. And the result of all the work that was done is the isoparametric elements. The isoparametric elements are elements that have that in the real in your model they live in X and Y. But this element comes from a perfect world with dimensions C and eta, and in the perfect world, the element looks like this. Not only this, the size of the element is, this is node -1, -1, -1, 1. Sorry, 1, -1. The nodes of the element all the elements that exist that have this 4 nodes have this parent element that live in a perfect world, and that has this shape. And the one thing is, we need to describe how I can relate this perfect world with the model. And you can relate it however you want to do. You can pick the centroid of the element and say it's this corresponds to this node. You can pick this one corresponds to this. So this is node 1, node 2, node 3, node 4. You need to pick a function such that node 1 corresponds to node A, node 2 corresponds to node B, node 3 corresponds to node C, node 4 corresponds to node D, the centroid corresponds to the centroid. However, now the best, or the isoparametric element utilize the same shape functions used, and that's why it's called iso, same parameters. So it uses the same shape functions to relate the model geometry with the element geometry, with the perfect world geometry. So basically, x, which is the horizontal component of the position, is equal to x1, m1, plus where m1 is a function of xc and eta, plus x2, m2, which is function of xc and eta. x4, so what does this do? Well, if you give me the coordinates of A, put here -1 and 1, sorry, -1, -1, -1, -1, -1, -1, -1, -1, -1. I'm sorry, this should be NA, NB, NC, N. The shape function A, B, C, and E. Because they're a function of xc and eta. So if you put -1, -1, NA will give me 1, and everything else will be 0, I will get the coordinate of x1. If you give me some point in the middle, it will be the average. X will be x1 and 1, x2 and 2, x3 and 3, x4 and 4. So basically you're going to get the average x in the middle. Because the point in the middle, you'll have a quarter of each. So this will be x1 multiplied by 4 plus x2 multiplied by 4 plus x3 multiplied by 4, x3 multiplied by a quarter plus x4 multiplied by a quarter. So you're getting the average of all of the x's, so you're going to get the average x in the middle. By using this, I am able to say I'm able to change the coordinates, and instead of performing the integration on x and y, then I can perform the integration on this beautiful domain from -1, -1 to 1 and 1. And not only this, the integration will be done in a numerical way, and we'll talk about the numerical integration in a second. So let's first look at how I will do this for one-dimensional elements. Now, you perhaps do not really need to do this for one-dimensional element. This is just for illustration purposes, just to explain to you how it's done. So, in the perfect world, or in the local coordinate system of the element, the nodes of the element have coordinates -1, 0, and 1. And n1, which is, let's call this node 1, node 2, node 3. n1 is equal to xc multiplied by xc minus 1 divided by -2. If you put xc equal to -1, so this is -1, -1, which is -2. -2 multiplied by -1. So this is +2. So n1 will be xc multiplied by xc minus 1 divided by 2. If you put here -1, you get n1 is equal to 1. n2 is equal to xc minus 1, xc plus 1, divided by -1. If you put xc equal to 0, 0 minus 1, 0 plus 1, you get -1 divided by -1. So n2 will give you 1 right here, and will give you 0 when xc is equal to 1, or when xc is equal to -1. n3 will be equal to xc plus 1 multiplied by xc. What happens when xc is 1? So when xc is 1, I get 2 multiplied by 1 divided by 2. So at xc is equal to 1, n3 is 1. At xc equal to 0, n3 is 0. At xc is equal to -1, n3 is 0. So you get, this is n1. This is n2. And this is n. And then the model world, the coordinate is equal to n1 x1 plus n2 x2 plus n3 x3. And so if I want to know what if I want to know what this point corresponds to in the model world, just input the parameter xc of this point, then you get the corresponding position in of the model. What is the point what is the model world of this point, and for this point xc is equal to -1. Put xc is equal to -1 in these functions, and you get that x is equal to x1. Now, we're also interested in dx by dx, because we're doing integration over small dx, and now we want to do the integration over dxc, so we're interested in dx by dxc. This will be x1, x2, x3, multiplied by dn1 by dc, dn1 by dc. Now, the rest, everything that you do after that will be function of these three numbers. So the rest can be done in a computer. The rest of the computations, we're just going to do it once. We don't need to do it again. All you have to do is just repeat, change the coordinates x1, x2, and x3, and everything else will just be function of those, the three coordinates of the element in the world. These three coordinates, I change those three coordinates, and I then obtain everything that I'm going to obtain right now. What is it that I'm going to obtain? I need to get the stiffness matrix. So basically, I want the stiffness matrix to be function of these things. Now, what I'm interested in is epsilon xx. This is what appears in my stiffness matrix, which is partial u by partial x. But I like to live in my perfect world, so I'm going to write u as u1 n1 plus u2 n2 plus u3 n3, which means I've written u as function of xc n, not as function of x. So how am I going to find partial u by partial x? Well, I'm going to find partial u by partial c, multiply this by dxc by dx. I'm using d instead of partial because we just have one variable here. And what's partial u by partial x? What's partial u by partial c? Well, partial u by partial c is equal to dn1 by dc. The nice thing is, all this, I mean, these are unknowns, but these will never change. Why will they never change? Because the coordinates of the elements will never change. These are engraved on this element forever. I'll never change these functions. So these I'll never change. So I'm going to call this matrix B, UB, multiplied by dx, dc, dx. So this is epsilon xx, the virtual work equation, or before the virtual work equation, epsilon star xx the virtual strain is simply epsilon x, but replacing UE with the virtual components, or with the variational components. U1 star, U2 star, U3 star, dx by dx. Or I can write it like this, U1 star. V transpose, let's write it. The virtual work equation is equal to sigma star. Oh, sorry, sigma multiplied by epsilon star, 1, 1, 1, 1, where xx, integrate over the area, the integrator of the volume of the element, which is area, multiplied by dx. The domain of the integration in the virtual work equation is the actual world, which is equal to A. Sigma on 1 is E. And then I'm going to put epsilon star on 1, epsilon on 1. And instead of dx, I would like to integrate in that beautiful world where everything changes from -1 to 1. But to do this, I have to multiply by a constant here to be able to change my integration domain. So, and of course, this will be equal to the integral. This is the internal virtual work. The external virtual work will be equal to U star multiplied by the distributed load over the element. Let's call it, what did I call it here? Q, integrated over dx. So, after you perform these calculations, and here you get U1 star, U2 star, U3 star, multiplied by your force, node of force vectors, and here you're going to get U1 star, U2 star, U3 star, multiplied by the stiffness matrix. So what is the stiffness matrix? And multiplied by U1, U2, U3. And from here we get that F is equal to K U. So what is the stiffness matrix? The stiffness matrix looks like this. K is equal to A, E, the integral from -1 to 1, epsilon 1, 1 star, so 3 by 1, 1 by 3, you get a 3 by 3 matrix. So the stiffness matrix will look like this. have a 3 by 3 matrix, all these entries, dn1 by dxc, dn2 by dxc, dn3 by dxc, these will never change. These numbers are constant for the element. These shape functions are constant. These will never change. These are engraved. The only thing that will change according to the element is this number, which is basically dxc by dx. This number or function will be function of, I'm going to go up, will be equal to 1 over this. And this is where the 3, x1, x2, and x3 appear. So when you program this element, I don't need to know anything other than this equation. And x1, x2, x3, I input them here, and then I do the integration. The integration is still a difficult issue. We have not discussed the integration, but that's what we will discuss at the end of today, how I will integrate from -1 to 1 this term. Now I'm going to do the same thing again, but for 4-node element. So how would I do this for a 4-node element? For a 4-node element, I have node 1 corresponds to node 1. Node 2 corresponds to node 2. Node 3 corresponds to node 3. Node 4 corresponds to node 4. And any vector here, because I need small vectors, will correspond to smaller vectors in the model world. So this is the model world, and this is the perfect world, where all the elements are square, and all the elements change from -1 to 1, 1. The first thing is I need to have a method by which both worlds will talk to each other. These are forever the shape functions in the perfect world. These will never change, because I've chosen the dimensions of the element to always be from -1 to 1, 1. So these will never change. To change between the two coordinate systems, I'm going to say that x is equal to x1 and 1 plus x2 and 2, which is equal to the sum of xi and I. And similarly, y is equal to the sum of yi and I. And so the rest will be function of those 4 numbers. Which 4 numbers? x1, x2, x3, x4, which are the coordinates of the element in the real world, and x2 and y1, y2, y3, and y4, the coordinates of the element in the real world. The rest can be then input into a program that's function of only those x1s and y1s, and to find your stiffness matrix. So, if this is the element in the perfect world, and this is a vector, let's call it dx, I'm interested to see where that vector is. Dx, this vector, is equal to the delta x, delta y. This is delta x, delta eta. I'm interested in the corresponding delta x and delta y. The corresponding delta x and delta y will be obtained by the form partial n, partial x, the partial capital X, sorry. By partial x by partial capital Xc, partial y, x by partial capital eta, multiplied by delta Xc, delta eta. Partial y by partial Xc, multiplied by delta Xc, plus partial y by partial eta, multiplied by delta eta. And this is called the Jacobian of the transformation. And this Jacobian of the transformation is what corresponds to, in the previous, corresponds to dx by dx in the one-dimensional case. Now in here you still see x1, x2, x3, x4. So in here you see the coordinates of the element. So J is functional, the coordinates of the element. Not only this, it will also be used to change my domain of integration, or the domain of integration. If I integrate over integrate over dx dy, this is equal to the integration of the determinant of j dx dx d. So if for me to replace dx and dy with the coordinates in the perfect world, I have to multiply by the determinant of this Jacobian of that transformation. Okay, so the rest we'll just do it once and for all, and we'll never have to do it again, because everything else is just done. It will be function of the coordinates in the perfect world. So in the perfect world, u is equal to n1 mi ui, sum from I equal 1 to 4, and v, the vertical displacement, is equal to the sum I equal 1 to 4 ni vi. So this will be equal to n1, 0, n2, 0, and so on. 0 and 1, 0 and 2, and so on, multiplied by u1, v1, u2, v2, u3, v3, u4, v4. These are the degrees of freedom of the element. I'm also interested in strains. The strains that I'm interested in are, in general, the strains in this coordinate system. But I'm going to write them in this coordinate system and then bring them to the world coordinate system. So first I'm going to write partial u by partial c, because I would need this to describe the strain. And partial u by partial eta, partial u, partial b by partial c, partial b by partial eta. This will look like this. dn1, partial n1 by partial c, partial n2 by partial c, multiplied by the degrees of freedom of the end. Partial u by partial eta will be partial n1 by partial eta, 0. Partial n2 by partial eta, 0, and so on. Partial b by partial c will be 0, partial n1 partial c, 0, partial n2 by partial c, and so on. And this will be partial n1 by partial eta, 0, partial n2 by partial eta, and so on. My strains, or the strains, are a function of partial u by partial x. Now, partial u by partial x is equal to partial u by partial, partial u by partial x. Partial u by partial x is equal to partial u by partial eta multiplied by partial eta by partial x plus partial u. Let me just write it. Start with x. So partial u by partial c multiplied by partial c by partial x plus partial u by partial eta multiplied by partial eta by partial x. Partial u by partial y will be equal to partial u by partial c by partial y plus partial u by partial eta by partial y. Partial u by partial v by partial x will be equal to partial v by partial c by partial x plus partial v by partial eta by partial x partial v by partial y will be equal to partial v by partial c partial y plus partial v partial eta by partial y. Okay. So if I make this into a matrix or a vector, it's equal to these. I can even write it as follows. I'm going to take here partial c by partial x, partial a by partial x, 0, 0, partial c by partial y, partial a by partial y, 0, 0, partial c by partial x, partial a by partial x, partial c by partial y, partial c. partial y multiplied by this vector partial u by partial c, partial u by partial eta, partial b by partial c, partial b by partial eta. So what did I do? These are the differentials with respect to the world coordinate system. These are the differentials with respect to the perfect coordinate system, the xc and eta coordinate system. Related by these. And what are these? This is j minus 1, the inverse of the Jacobian of the transformation. So again, I'm going to move up. This is j, which relates vectors in the world coordinate system with vectors in the perfect coordinate system. The inverse of it, I'm going to use it to relate differentials in the perfect coordinate system with differentials in the world coordinate system. Now, why am I doing all this? What I'm interested in is the following. I'm interested in epsilon xx, which is partial u by partial x. Epsilon y, which is partial u by partial y. Sorry, partial b by partial y. And I'm interested in gamma xy, which is partial u by partial y plus partial b by partial x. These are what I'm really interested in, because these are what will appear in the virtual work equation. So I can just put here a matrix 1, 0, 0, 0, 1, 0, 1, 1, 0. Put here partial u by partial x, partial u by partial y, partial b by partial x, partial b by partial y. What did I do? Epsilon xx is equal to this multiplied by this. I get partial u by partial x. Epsilon y is partial b by partial y. Multiply this by this. You get partial b by partial y. Gamma xy is equal to this. Now, I can replace all these partial u by partial x, partial u by partial y, partial b by partial x, partial b by partial y. I can replace it with this vector, which is function of this vector, which is the derivatives in the perfect coordinate system. And the derivatives of the perfect coordinate system are a function of the degrees of freedom of the element. And so this will be equal to a huge matrix B multiplied by UE. And this will be the degrees of freedom. And this matrix will be 3 multiplied by the degrees of freedom. And so the virtual work equation would look like this. From -1 to 1, from -1 to 1, B transpose CB, multiplied by the thickness. I'm integrating in the perfect coordinate system, so I have to multiply by the determinant of j. This will be equal to -1, -1 to 1, -1 to 1. The integral of n transpose will be determinant of x, the determinant of j dc d eta, where b is equal to b1, b2, plus the integral of n transpose Tn integrated over the surface of the element. Now, if you ever have to program this, you have to be very careful, because n is a function of xc and eta, yet the virtual work equation, this is a function of x and y. So we have to replace the surface with equivalent xc and eta. And you have a problem in your book where all of the above has been input into a Mathematica software, Mathematica code. All you have to do is just change the coordinates of the element and the stiffness matrix comes up. So all you have to do is just change x1, x2, x3, x4, y1, y2, y3, and y4, and everything comes up. Now, usually now all the softwares do the meshing automatically. But if you program this, or if you input the mesh by hand, and if for whatever reason you define your elements x1, y1, x2, y2, x3, y3, x4, y4, the software will issue a warning that will not continue, because it will tell you that the area of this element is negative. How will it know that the area of this element is negative?
Because you labeled the coordinates.
So how would it know? What's the calculation? We're only doing 2D here. There's no cross product. Where in the above? That's, see, the problem, I can't say cross product because I'm doing 2D here. But you're right. I mean, you're right if you add the third direction. So how does it know?
It always does like 2 minus 1.
So where is that? It's right here. It's right here. The determinant of this matrix. If the determinant of this matrix is negative, it's the opposite orientation. If the determinant of this matrix is positive, I'm in the same orientation. Now this is the same for higher dimensions. The difference is now you can use the same shape functions to model curved elements with curved surfaces. You don't have to stick with, so if your geometry have curved surfaces, you don't have to stick to elements with only straight sides. You can model elements with curved sides by following the same shape functions. And so in the perfect world, the element is square. I'm integrating in the domain from -1, -1 to 1, 1. But the element in the model world exists in this new coordinate system, in the world coordinate system, with the following shape. Of course, it's very important that if you're using software and you're inputting the coordinates of the elements manually, you have to define. Now the software does it for you now, but during my time when I used to do FEA, I had to say this element is defined from these particular nodes. So I had to input the order of the nodes in the correct manner. Because if this is node 1, node 2, node 3, node 4, node 5, node 6, node 7, node 8, this is how I should input. The order has to be according to the convention in that particular software. Because that particular software, this is 1, 2, 3, 4, 5, 6, 7, 8, then this is how I should input the nodes, the corresponding nodes as well. The general triangle element, this is the isoparametric shape of it, and the triangular element, you can model a curved shape with a triangle, and in the perfect world coordinate system, it looks like this. So now what we need to do is solve the last issue, which is the integration. So I'm going to go up again. And look at this. I want to be able to integrate this that has the determinant of j in it from -1 to 1, -1 to 1 on a domain dx d eta. Now let's look at the determinant of j, because it's important to see that the determinant of j has functions of partial x by partial xe, and so it has the derivatives of the shape functions with respect to xe and with respect to eta. You also have inside, so inside here these are functions of partial x by partial c, partial n by partial c, and partial n by partial eta. Inside here you have functions of partial of 1 over partial n by partial c and 1 over partial n by partial eta. Where did these come from? These came from the inverse of the Jacobian of the transformation. So this can get complicated. So what I want to say is that this can get very complicated to do the integration, especially if your element is skewed. If your element is skewed like this, you'll get fractions. Here you're going to get fractions, and it will be very hard to integrate from -1 to 1. And so we're going to utilize a numerical integration scheme, and that numerical integration scheme is called the Gauss integration scheme. The Gauss integration scheme is a simple integration scheme that works really well for elements that are close enough to the actual shape of the element. So the Gauss integration is a numerical integration scheme that works well for elements that have a shape close to the shape in the perfect world. understand the Gauss integration in one dimensions first, and then extend it to our elements. So we have defined function from -1 to 1. So basically I have a function defined from -1 to 1. So this is xc. The purpose of what I'm trying to do is to find this area. Because I'm trying to integrate f dxc from -1 to 1. So in general, a numerical integration scheme allows you to calculate the following. So if I have a function integrate from -1 to 1, usually you can replace that sum by this integral with a sum, let's say from I equal 1 to n, f of I multiplied by delta xi. So delta xi multiplied by fi. This is in general what a numerical integration scheme does. I can look at it as if it's equal to the sum, I equal 1 to n, f of xi multiplied by a weight, where this is x1, x2, x3, x4, x5, x6, x7. These are different points, and each point is multiplied by a weight. This weight happens to be delta x, delta c. I can call it the weight corresponding to point I. So this is Fn, let's say Fn, and this is the weight corresponding to point n. Now let's see what happens if f is linear. What if f is linear? I'm going to replace -1, 1, f dxc, -1, 1. When f is linear, f is equal to a naught plus a1x, a1c. I'm going to replace this, so this will be a naught multiplied by c, -1 to 1, plus a1 c squared over 2, -1 to 1. This will be equal to 2a naught plus a1 multiplied by 0. This is equal to 2a naught. I could have replaced, instead of actually doing the integration, I could have said, you know what, this is equal to f of 0 multiplied by 2. Because f of 0, this is f. So basically, instead of actually doing the integration, instead of trying to calculate this area, it's drawn at the bottom here. Instead of trying to calculate this area, and integrate a0 plus a1x from -1 to 1, I could just calculate the function at 0 and multiply by 2. And this is a numerical integration scheme because I'm not really doing any integration. I'm calculating the function at a point, multiplying by a weight. But this happens to be accurate when the function is linear. If the function is quadratic, cubic, this is equivalent to say I would like to calculate, this is the integral of this function from -1 to 1 is equivalent to calculate the function, the value of the function at 1 over square root of 3 and 1 over square root, -1 over square root of 3, and the weight is 1 and the weight is 1. Here the weight is equal to 2. Now here's a question. If I use this integration scheme to calculate this, would it be accurate or not? If I use this one to calculate the linear function, would it be accurate or not? Yes, it will be accurate because the linear is is already included here. So if I use this integration scheme to calculate a lower a function that has a lower order, I'm still getting accurate results. The difference is I'm doing more calculations than I need. Here I'm calculating f at 2 points and adding. Here I'm calculating f at only 1 point. This point, or those 2 points, are called in finite dimensional analysis, they are called the integration points. These are the points that I'm using for integration. I'm not really doing any integration, I'm actually calculating the function at this point, and then multiplying by a weight. So this is called the integration point. And if I'm using one integration point, the corresponding weight is 2. If I'm using 2 integration points, the corresponding weights are 1 and 1. If f has a 5th order polynomial, the numerical integration scheme that would actually produce accurate results is the 3 integration points. Integration points are root 6, -root 6, and 0, and the weights are 5 over 9, 8 over 9, and 5 over 9. So for first degree or lower, I need one integration point. This integration point exists at x1 equals 0, and the corresponding weight is 2. Third degree or lower, the number of integration points is 2, and the integration points exist at x1, 1 over 3, and x2 over -1 over 3, and the weights are 1 and 1. And the 5th degree or lower, 3 integration points, and these are the weights, and these are the corresponding integration points, or the integration points and the corresponding weights. Now, this works really well if I have a function that is a polynomial. The stiffness matrix that we obtain is actually not a polynomial. It is, we're going to go back. What we're trying to do now is to integration of this matrix that we have, integration of each component. This will be a polynomial, but this will be a fraction. As long as this fraction is close enough to a polynomial, it's fine. So this numerical, because I'm going to utilize this numerical integration scheme to integrate this. So instead of actually doing the integration, I'm going to evaluate this at particular points and multiply them by weights. So as long as this is a polynomial, it's fine. But once it's not a polynomial anymore, if this gives me 1 over c minus theta, if this is close enough to c power 5, then sure, 3 integration points would be good. But if this cannot be approximated by something like this, then the numerical integration scheme I'm using is not very good. I think I'm jumping ahead, but basically we're utilizing this numerical integration scheme to calculate, to integrate the stiffness matrix. And what I'm showing you here is that this numerical integration scheme will give you accurate results. You're not really, it's called numerical integration, but you're actually obtaining the accurate results if your function is a polynomial, a linear, first degree or lower, third degree, or fifth degree. Now, how would you come up with the following, or with the above? You basically solve a few equations in a few unknowns. So for example, we need to verify that the exact integral of a general cubic polynomial on the interval from -1 to 1 can be obtained by the two integration points x1 and x2 with the two weight functions w1, w2 equal to 1. So basically I want to verify that this is true. So a general polynomial of the third degree has this form. I'm saying that this is equal to a function, the function at a point, integration point x1 multiplied by corresponding weight x1 plus a function at a point x2, the function at a point multiplied by a corresponding weight w2. And I would like to know x1, w1, x2, w2. So this is equal to A0 plus A1 multiplied by 0 plus A2 over 3, here's 2, multiplied by 2 plus A3 multiplied by 0. This is equal to W1, f of x1 is equal to A0 plus A1 x1 plus A2 x1 squared plus A3 x1 cubed plus W2 A0 plus A1 x2 plus A2 x2 squared plus A3 x1 x2. So for a general cubic function, these will vary. So you have one cubic function where A3 is 1 and everything else is 0. For another cubic function, you can have A3 is 1 and A2 is 1 and A1 is 0 and A0 is 0. So how many equations, to make sure this work for every A0, A1, A2 and A3, I have to make sure that the multipliers of A0 on the left have to be equal to the multipliers of A0 on the right. So first equation, W1 plus W2 is equal to 2. Multipliers of A0. Multipliers of A1, 0 is equal to W1 x1 plus W2 x2. A2, something is equal to 2 over 3. W1 x1 squared plus W2 x2 squared. And finally, W1 x1 cubed plus W2 x2 cubed equals 0. From this, you get W1 is equal to W2 is equal to 1, and x1 is equal to 1 over root 3, and in x2 is equal to negative 1 over root 2. So I have found 2 points, I call them the integration points, and 2 weight functions that will give me exactly the integral from negative 1 to 1 of any cubic function. So if I have any cubic function, all I have to do is just calculate that function, 1 over root 3, negative 1 over root 3, multiply by w, and get the numerical integration. Or in this case, it's an exact integration. Now what if I have 2 dimensions? Now this works for 1 dimension. If I have 2 dimensions, I have f of x and y that changes on x and y, and the domain of integration is from negative 1 to 1, negative 1 to 1. This will be equal to negative 1, 1. The sum I equal 1 to n f of xi y multiplied by the corresponding weights. So doing the numerical integration along x first, and then doing the numerical integration along y. Okay, so how does this apply to the finite element analysis? So I'm going now to utilize this integration scheme to calculate the stiffness matrix by, instead of integrating on my whole domain, I'm going to calculate the entries of the stiffness matrix at particular points, and these particular points are the integration points. So for the 4-node quadrilateral, I have 4 integration points, simply because f of x and y is quadratic. We know that the strain here is linear, and I'm calculating the strain. I know that the strain is linear, and I'm calculating the strain squared, or I'm integrating the strain squared, and so the function is quadratic. Because the function is quadratic, the best way to calculate this, so here the strain is linear, so the strain squared is quadratic. So for quadratic functions, for 3rd degree or lower, 2 integration points are good enough in 1 dimension. So 2 integration points in each direction are good enough, and the coordinates of the point are negative 1 over root 3. Negative 1 over root 3. 1 over root 3. Negative 1 over root 3. And so on. So the stiffness matrix in this case is equal to 8 by 8. Now, how many calculations do I need for the stiffness matrix? If you just calculate so for each entry, I need 4 calculations. And then adding them together, because I need to calculate this entry at this point, and then this entry at this point, this entry at this point, and this entry at this point. And so I get 4 calculations, and each multiplied by its weight. Added together, you make the stiffness matrix without actually doing the integration. You're doing a numerical integration. For the non-linear I have 9 integration points, 3 in each direction, and the location of the integration points are according to the location of the integration points are according to this table. And so you get 3 points by 3 points, so 9 points in total. So K, which is equal to 8, this is the degrees of freedom are 16 by 16. Each entry is calculated 9 times. So here, calculations. 16 by 16 by 9 times. Here, so total. Eight by 8 by 4. So to form the stiffness matrix, I need 8 by 8 by 4 calculations, and excluding the additions. And to form the stiffness matrix for a nonlinear element, I need 16 by 16 by 9. This is called full integration. Any element that is done this way is called full integration. And the elements that we utilized for the previous assignment is the full integration element utilizing exactly this scheme. The first thing you did in your software is this what you used, or you don't know which one you used? So the first, when you clicked on the element, there was something called reduced integration, and you click on or off. So what happens when you click on reduced integration? When you click on reduced integration, you tell the software on reduced integration, you tell the software for this element, which requires 4 by 8 by 8 calculations, instead of using the full integration, use the reduced integration version, where do the calculation once. Utilize only this. So 1 by 8 by 8, and what does it do? For now, it just reduces the calculations. For now, all we see is that it reduces the calculations, and of course loses some accuracy. So lose accuracy. But faster computations. Because I've reduced the number of computations 4 times. And for the non-linear version, when you click on reduced integration, instead of 1, 2, 3, 4, 5, 6, 7, 8, 9, instead of doing the integration 9 times, or the calculations 9 times, you utilize the less order, so 4 integration points. So instead of 16 by 16 by 9, use 4 by 16 by 16 calculations. Loss of accuracy, but faster computations. So this is what you need to do for the next assignment. You have to now click on reduced integration and see what happens. So what are you going to notice? You're going to notice the following. You should notice that this is the solution that you're looking for, and this is the number of elements. The previous assignment gave you a displacement that looks like this, and the next assignment should give you a displacement that looks like this. which means the reduced integration makes the structure more flexible. But the problem with reduced integration is that if you use a very fine mesh, and this we will discuss next time, what happens when you use only one element per thickness of your beam? If you use one element in the thickness of the beam, what happens to the displacement? And two, if you look at, so try to read the rest of the chapter, and we're going to continue next time. But what you will find is, when you use for node one layer, look at the displacement, you're going to get very large displacement. So this is what you should get as well, something huge when you use only one layer of element and trying to model it under bending. And we will discuss why this is the case in the next lecture. All right, you guys have any questions? All right, you're free now.